Hello and welcome to our presentation on multiple model adaptive estimation Kalman filtering. Okay, so to introduce the topic, the goal of this project is to develop a practical application of a multiple model adaptive estimation Kalman filter to estimate the state of the system. In this case, it will be the linear carriage position. So we're going to use different position estimation methods using acoustics and accelerometer data on the to track and measure the linear carriage. And then we're going to compare that to an encoder, which is on the motor, which will give us a real kind of estimation of the position of the carriage. So an application of this could be tracking an object that's difficult to measure in real life scenarios. And then using that position estimation, you can then put that into a controller. Okay, moving on to our system model. So we are going to be using a combined measurement model, which uses both accelerometer and acoustic sensor data to describe the system. So this is the state space representation of the system, using the equations of motion to model the platform as a particle. So as you can see in the measurement matrix, we have X is the position measured via the acoustic triangulation method using the ultrasonic sensors. And then X double dot is the acceleration, which is measured via a IMU, which is on the platform. Okay, so just to show a simulation of this Kalman filter method, we have a simulation here of some incoming data, which may be very noisy. And we're using a step input to kind of show what the position might be after filtering. As you can see, the estimated position from the combined Kalman filter is good, especially during the kind of stationary areas towards the end of the time. Okay, moving on to the theory of multiple model adaptive estimation Kalman filtering. So it's a technique for estimating the state of a dynamic system. And it does this by combining several KFs together, and this improves the estimation accuracy. So each KF model represents a different dynamic model of the system, and then a selection algorithm is run, which chooses the most accurate models, the models with the least residual. And this is very useful, especially for systems with changing dynamics and unknown model parameters. So in this project, we're using the Kalman filters for signal processing and not in a state space controller. So we couldn't really investigate the stability, controllability, and observability of the plan.
And so for our application, you can see here, this is our physical setup that we built. We have three different methods of determining position physically. First, we have a DC motor here, which has an encoder attached. That's attached to this linear screw, which allows this platform to translate back and forth. We're trying to determine the position of this platform, like the center line right here. The first method for positioning that we are saying is the true method is using the encoder to count how many rotations have happened and translating that into linear position using the pitch of that screw. And then the two methods we're using to estimate position, which are more realistic to say like having a car driving down a road where you don't know the true position because it's not attached to a linear screw, are one, acoustic positioning using the receivers here and the transmitter on the left here, which basically send out a pulse from the transmitter received at the receivers at different times, that time of flight, using some simple geometry, knowing this horizontal or this vertical distance, you're able to determine the position of the platform using that time of flight data. The third method is using this IMU here, which is at every given point giving you an acceleration reading in this X direction, which we're defining as the direction of the linear screw. If you integrate that acceleration twice, we can get position. So those are our three basic methods of getting position. So in order to make the data collection and position estimation better, we are applying the MMAE model. We have three Kalman filters in our system. First is the combined model, which combines both the acoustic position and the accelerometer acceleration readings. That's a 3x3 system, and that was a system that we showed in the very beginning. Next, the two simpler models we have are one model, assuming we just know the acoustic position. So this is a 1x1 model. And one model assuming we just know the acceleration or accelerometer position, which is the acceleration from the accelerometer integrated twice to get position. Those are both position measurements and they're both 1x1. So in total, we have three Kalman filters that output an estimated position. We then apply an MMAE to it, checking the residuals and weighing each filter's output by the accuracy of its residual. Note that the residual is not the difference between the estimated position and the true position, because these filters have no idea that the encoder position exists. The only reason we're using encoder position is to say this is our true position and to weigh it, or to calculate percent error and determine which filter is the best. The residual is just within the filter itself. So you can see here, these are some videos of our system in operation. On the left-hand side, you can see here, this is our platform moving back and forth. It's a little bit hard to see, but I'm manipulating a slide potentiometer there, which we're basically reading, and we have a state space controller that's positioning it. That's just to allow us to be able to move the platform to different positions and know where that position is to test the accuracy of all of our different position methods. And on the right here, you can see this is how we automated some of our testing. We just had the motor go back and forth, knowing its position at each point by reading the encoder, and then measuring, or like seeing what each filter or positioning method said its output was supposed to be. So if you go to the, we can go on the next slide here. And you can see the measured output. So this is the result of our program that we wrote in C++. Every 2 seconds, it would print a different output for a different instant in time. So for this particular measurement, it says that for this data set, the acoustic time of flight positioning method is the best. So we, in total, have 6 positioning methods that are estimations. First is just the raw accelerometer position. This is integrating the accelerometer twice and assuming that that's the position. Second is just the raw acoustic position. So this is just taking data from the acoustic sensors and determining the position from that. Third is the accelerometer position, but passed through a Kalman filter. Fourth is just the acoustic position data passed through a Kalman filter. Fifth is the combined acoustic and accelerometer data. This is the model we showed in the very beginning, run through a Kalman filter. And last is the MMAE, which takes all those 3 previous Kalman filters and puts them into one. You'll notice here that the acoustic time of flight is the best on average through lots of iterations. And in this particular data set, with the Kalman filter is the best on average, and just the acoustic raw data is the best for this simulation. And on the bottom there, you can see the proportions used for the MMAE. It's using about 50% of the data from the accelerometer Kalman filter, about 46% of the data from the acoustic Kalman filter, and only about 4% of the data from the combined model that we had in the beginning. But you'll also notice that the Kalman filter acoustic position only has a percent error of 5%, but the accelerometer position, which is weighted more heavily in this MMAE, is off by around 57%. So even though the MMAE thinks that that's a better measurement, but in reality, the acoustic one is. So if we take a look at some plots that we made, this was a result of that second video that you saw, moving the platform back and forth. We basically just took a bunch of different measurements, moving that platform back and forth a lot of times and plotting them. These are all 6 of our positioning methods. You can see that the accelerometer, any measurements that had to do with the accelerometer. So accelerometer position with the Kalman filter has a really big spike there in red. The raw accelerometer position is pretty noisy and it's pretty far from the dotted line, which is our true position. The acoustic data, both the Kalman filter and the raw data, seem to track fairly closely to the line. And then the combined Kalman filter somewhere in the middle, and the MMAE is there as well. That tracks pretty well with what we saw in that last output, where the acoustic is a little bit more accurate than the accelerometer. So the reason for that is because our accelerometer is not giving us proper data. We did not properly filter the data from the IMU. We are just using the acceleration in one dimension. And we're not accounting for the fact that, like, when the system is moving, the accelerometer might be turning a bit and some parts of gravity might be affecting the acceleration readings. So the accelerometer is less noisy, which is why the MMAE wants to weigh it higher, because the measurements that it's expecting are very close to the measurements it's getting. It's just that the measurements themselves are wrong. So for this, we're just going to analyze the acoustic data. So here you can see the acoustic data passed through a Kalman filter and then raw, and then plotted against the true position. You'll notice in the graph on the left that the acoustic data, the raw data, seems to be more accurate than the Kalman filter data. And for this moving example, it is. Note that on the left, these data points were all taken when the system is in motion. However, on the right is a stationary position graph. We set the position at one point, didn't move it, and just took up data over time. For that case, the Kalman filter is a lot more accurate. Notice there's still a little bit of an offset, but that's just a calibration issue. The raw data is much more noisy in the stationary position, and the Kalman filter gives a better example or better result. And since the system was designed to be mostly stationary and not moving all the time, that's why that Kalman filter works better there, because that's what it's designed to do.
So the last plot that we'd like to discuss from our results is the output proportions and how often the MMAE algorithm weights each type of Kalman filter at its different value. So you can see here that it varies, but it's often using upwards of 40% of the acoustic data, which is in the green line. And you can see that the accelerometer is all over the place and the Kalman is kind of somewhere in between. But this is a good example of the use of a MMAE, which can be explained by something like an airplane wing accelerometer, where there's a lot of different types of noise input, which could come from, in our example, vibrations of the wing due to the plane itself vibrating, or vibrations in the, or noise in the accelerometer from wind or other types of noise error that could come in there. And that's where the MMAE excels, is in taking in all of the different types of noise and being able to still output a valuable measurement at the end. So comparing to some classical methods, now we didn't exactly do a controller in all of this. Our main project was filtering the output data, and that's what we decided to go with. So we're not going to talk about comparing to controllers, but we can talk about comparing to more primitive methods of noise filtering, which could be a low pass or a high pass filter. And you could see that in our case, that wouldn't work very well because our noise is all over the place. We're not just having noise in a certain frequency range that's either really high or really low. So this Kalman filter does an excellent job of filtering noise from all different areas. And that's why I wanted to redisplay this graph here, where it shows how well the Kalman filter performs compared to raw data in the case of the acoustic. And you can see really how valuable this would be. Now, MMAE Kalman filters are superior due to system adaptation and being able to predict a more accurate reading with each time step. So it's basically learning and becoming a more accurate estimator as time goes on. And this allows for, like I mentioned on the last slide, multiple different noise states. That's the whole point of the MMAE, where you can use all the different noise state models and still get an accurate estimation at the end. Now, in conclusion, MMAE Kalman filters are very effective in combining multiple measurements in systems with high variability. You can see an example of what the MMAE looks like on paper on the right side here. And MMAEs can be implemented in real time, which is a huge advantage because we were able to see how well the filters were working instantaneously, and we didn't have to wait for post-processing of the data. We could see how they were performing with each time step as the measurements were being taken. Applications for MMAE Kalman filters are very broad, but they include primarily GPS, navigation, and missile guidance, and many other sorts of applications. But MMAEs, we believe, are an important advance in signal processing and estimation theory and have lots of potential in the world to come. And we really enjoyed getting to learn more about them throughout this project. Here's some of our references, and we thank you for your time.